Okay, in this application, we're going to look at applying rational equations to another type of distance problem. So in this situation, a speedboat, which moves at 40 miles an hour in still water, travels 7 miles an hour downstream in the same amount of time that it takes to travel 4 miles upstream. Find the speed of the current. So I previously explained that you would learn two types of distance problems. Type 1 was when the times were equal, and type 2 is when the times total. You have to add the times together. Notice in this problem, it literally tells you in the same amount of time. So that tells us that we are actually going to use time 1 equals time 2. And so in this case, we are going downstream versus upstream. So we're going to spend the same amount of time going downstream as upstream. Now the situation is when you're going downstream, the current is going to make you go faster. So therefore you would go further downstream in that same time, as opposed to going upstream where you're going against the current. It's going to slow you down. So you wouldn't be able to go as far upstream in that same time frame. We know that distance is rate times time. So if we've solved that for time, we could get distance divided by rate. So time I could substitute with distance divided by rate. I can bring those down. And the downstream distance, it tells me, is 7 miles an hour. The upstream, it tells me, is 4 miles. I'm sorry, not 7 miles an hour, just 7 miles. Now my speed or my rate, it tells me that the boat is automatically going 40 miles an hour in still water. But when you're going downstream, the current, like I said, is going to make you go faster. So we want to add the current to our speed to make us go faster. When you're going against the current, when you're going upstream, it's going to slow you down. So instead of going 40 miles an hour, you're going to go slower than that. Notice that this is a rational equation. So we're going to look at our LCM. And in this case, it would be 40 plus C and 40 minus C. And excluded values. Excluded here would be if we got 40 or negative 40. I guess technically I was using a C this time. So if the current was negative 40 or positive 40, that would be a bad thing. It would give us an extraneous solution. So let's take our problem. And we're going to multiply by the LCM on both sides. So distribute that to both fractions. And we'll do it over here. Now the whole point of doing this, again, is so that some of the fractions or some of the factors can cancel, leaving us no fractions. So these two are gone, these two are gone. So I'm left with 7 and 40 minus C and 4 and 40 plus C. So if we do some distributing here and go ahead and just solve it from this point on, if I subtract the 160 over, I'm going to get 120. If I add the 7 over, that will give me 11C. And if I divide that, I'm going to get about 10.9 is the speed of the current. So 10.9 is not 40 or negative 40, so that's a good thing. So kind of what this means is when you're going downstream, if I go downstream, remember that was the 40 plus the current. So 40 plus 10.9 means we're going about 50.9 miles per hour. Whereas upstream, we're subtracting that 10.9. So we're getting about 29.1 as our speed. So big difference going upstream versus downstream. So two types of distance problems. This was the second one that we've done. Make sure you're double checking and be careful with all those distributing. I know it looks a little complicated, but if you kind of use some common sense, it's really, it can get manageable for you.